Hi, in this video we are going to talk about another application for the stacks, and basically we are going to consider that what's the connection between the stack abstract data type and recursive method calls. So there are several situations when recursive method calls are quite handy. For example, graph traversal algorithms such as the depth-first search, or traversing a binary search tree, or looking for an item in a linked list. And you may pose the question that, okay, what's happening in the background for recursive method calls? And basically all the recursive algorithms can be transformed into a simple iterative method with stacks. So it's very important that if we use recursion, then the operating system is going to use stacks in the background, no matter what. Okay, we use recursion, we talk about recursive method calls, but the operating system and the central processing unit is going to use the call stack, as we have discussed in the previous video. For example, we have the famous graph traversal algorithm, the depth-first search, and we are able to implement it with the help of recursion as well as with the help of iterative approach. So as you can see, as far as the recursion is concerned, it's going to store the method call, and this method call is going to call itself. So we have to check whether the given vertex is visited or not, and if we haven't visited that given node, we are going to call the same method recursively on that given node. And basically, this recursive method call can be transformed into a while loop, and in the while loop we have to use a stack. We have to iterate until the stack is not empty, and we just have to push vertices to the stack. So this is how we are able to transform a recursive method implementation into an iterative approach, and the iterative approach into a recursive implementation. So for example, let's consider the factorial algorithm with recursion. This is the function with the recursive implementation. And I'm not sure whether you are familiar with the factorial, but the definition is that n factorial, we usually denote it with exclamation mark. So the n exclamation mark is equal to n times n minus 1 times ... 2 times 1. So for example, the factorial of 4 is going to be 4 times 3 times 2 times 1, which is equal to 24. And it's very important to implement this factorial function with the help of recursion. For recursive algorithms, we have to have a base case. And basically, if n is equal to 0, we return 1. This is the base case. The factorial for 0 is equal to 1. Anyways, we return n times the factorial of n minus 1. And it's going to be the implementation for the factorial. So what does it all have to do with stacks, you may pose the question. The recursive function calls are pushed onto the stack until we bump into the base case. What's the base case? That if the n is equal to 0, we return 1. So the factorial of 0 is equal to 1. And we keep backtracking when we hit this base case, and we know the base case, so we know the sub-solutions. And if there are too many function calls to be pushed onto the stack, then the stack may get full and no more space left. This is what's called a stack overflow error. And you are able to make this kind of stack overflow error if you forget to implement the base case into your factorial function. I'm sure that every one of us who used recursive method calls knows about stack overflow. I have had several stack overflows in my life, so if you miss the base case, then you are definitely going to use a stack overflow, because the algorithm is going to run forever. I mean, not forever, because the stack is going to get full, and if it's full, of course, then the stack overflow is going to come. Okay. So this is how we implement the factorial in a recursive manner, and we would like to calculate the factorial 4. We don't know the factorial 4, so we are going to push it to the call stack. But we are able to reduce this problem into a subproblem, because we just have to calculate the 4 times factorial 3. This is not the base case, so again we are going to call the factorial function with the integer 2. 3 times factorial 2. Then we are going to call the 2 times factorial 1. Then we are going to call the 1 times factorial 0, but the factorial 0 is equal to 1. 1 times 1 is 1, so we return 1 because we hit the base case. And basically, from now on, we are going to backtrack. We are going to replace the sub-solutions into the method calls, and that's how we are able to calculate the factorial 4. So we are going to return 1, and then we are going to substitute 1 here. 2 times 1 is 2. We are going to substitute 2 times 1 here. We are going to substitute 3 times 2 times 1 instead of the factorial 3. And then we are going to have the solution. So the result is 4 times 3 times 2 times 1, which is 24. So the conclusion is that recursive method calls are going to be piled up in the stack. And if the size of the stack is not that great, and for example the depth of the recursion is huge, then we usually get a stack overflow. And that's why, for example, calculating the factorial of 1,000,000 is not going to work fine, because we are not going to be piled up as many function calls in the stack as we would need to calculate the factorial of a huge value. So I think that it is pretty interesting to see that how recursive method calls work in practice, and what does it have to do with the call stack. And basically this is how function calls can be piled up in the stack. And we calculate the sub-solutions, then we have the base case, and we are able to substitute these solutions into the sub-problems until we bump into the first method call, and then we are able to return with the value as we have seen for the factorial 4. So that's all about recursive method calls and stacks. Thanks for watching.